Hello everyone, we are in section 14.3. In section 14.3, we're going to look at geometric sequences and series, continuation of our work in chapter 14. Coming out of section 14.2, the section prior to this, we looked at arithmetic sequences and series. So in this section, we're going to look at another type of sequence and series, namely geometric. So here's an image of a page of the book. The highlighted problems are the ones that are you doing for your homework. The ones with green dots next to them are the ones that we're going to actually look at in this lecture, and we're going to work them together. Okay, so let's actually begin with this section. Now here I have made up a sequence. Okay, so the sequence, as you can see, starts with number 5, then it goes to 10, 20, 40. So this would be my A1, A2 second term, third and fourth term, and so on. This is an infinite sequence, right, because of the dot, dot, dot. Now, something special about this particular sequence I made up is that if you take a look at how we go from, let's say, 5 to 10, from 10 to 20, 20 to 40, each time we multiply the previous number by 2. Right, to get to the next number. So there's actually a constant rate in here, constant rate of increase. So again, if you multiply 5 times 2, you get 10, 10 by 2, you get 20, and so on. So one way I can write this relationship is as follows. I can say A2 is 2 times A1, right? And A3 is twice A2. To get to the A4, well, A4 is twice A3, right? That means you multiply the third term by 2 and you get to the fourth term. Now, if I kind of unwind this and go backwards, that's 2A3. But then A3 itself, remember A3 is twice A2, correct? And as it's shown over here, twice A2. So here I get 2 squared times A2. I know that's 4, but in this section, we're very interested in the patterns that we see. Okay, and let's see. What about A2 itself? A2, again, A2 is now given up here. It's twice A1, so I'm going to write that as 2 times A1. And this makes this 2 cubed times A1. The idea is to write the fourth term in terms of the first term. In fact, every term in terms of the first term. So I can now kind of conclude that A4 is 2 cubed times A1. So one thing that we immediately note in here is this. For the fourth term, where the subscript is 4, the exponent on 2 is 3. Right? So that's what it turns out to be, which is 1 less than the term number, right? 3, 1 less than 4. So if I expand on the pattern that I see here, I can write this sequence again as I have it up here, just the way I have it right up here. I can continue writing this as the following. I can write this sequence as A1, A2, A3, dot, dot, dot. At some point, I'm going to have, let's say, the nth term. And then the next term is n plus 1. Next one after that would be n plus 2, and dot, 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 and so on and so forth, right? Now, using this example as inspiration, then we can actually see now how to go, remember, from one term to the next term. So again, for example, to go from 20 to 40, we multiply 20 by 2. That constant rate, which in this case turns out to be 2. So I'm going to write it as following. The nth term, therefore, is going to be the one before it times a constant. That constant rate, we're going to call that R. Okay, so that's what I'm doing. I'm multiplying by that constant rate R. I hope you're following so far. Okay, and then from this, what I can do is if I solve for R, divide both sides by n minus 1, and I get a n over a sub n minus 1 is R. Okay, now if I use, let's say, the n plus first term, I can get n plus first term by multiplying the nth term times r. And from this I get r is equal to a sub n plus 1 over a sub n. Same constant rate. Okay. Now notice that the ratio of the nth term to the n minus 1 would be the term before. Okay, it's like, where's n minus 1 here? That's actually, it would be over here. This is a sub n minus 1. All that means is that that's the term before the nth term. Okay, so I can get this common ratio as long as I divide two consecutive terms. Okay, the higher term divided by the lower term. So for example, I can get the common ratio by dividing a3 by a2. I can get the common ratio by dividing a2 over a1. It doesn't make a difference because it's common. Okay, so that constant rate r is called a common ratio. Okay, now based on what we have seen here, and let me just kind of use this one as my example, then we're going to go to the book's definition of what a geometric sequence is. So a sequence is geometric if there is a number r. This number r, they're going to call it a common ratio. Remember, that's that constant rate that I talked about. So that if you divide n plus first term by nth term, it's going to be r. And what they're using here is in fact what I have here. That's what you see in here. Okay. Now this other part of it, which is this part now, right in here, this says the next term, a sub n plus 1, is a sub n, the previous term, times the common ratio. That resembles what I have up here. Okay, so these are just two different ways of writing the same thing. Now, anytime we define one term in terms of another term, so here's n plus first term defined in terms of a sub n. That would be the nth term. So anytime we define one term in terms of another term, then we call that the recursive definition. So this geometric sequence here, the book gives you what we call a recursive definition of what a geometric sequence is. Okay. Now, let's actually take a look at another form. The form we are interested in is actually another form. Okay. Now, let's continue on here. So here's my first term, a sub 1. And remember, the second term here can be written as a constant rate times the first term. The third term is going to be r times the second term. The fourth term is going to be r times a3, and so on, right? So if I continue on this pattern, therefore, what do you think the nth term would be? Okay, well, again, drawing inspiration from what we did earlier, remember a2 here, this a2, we have it over here. That's the same a2 here. So I can write this as r times r a1. That's a3. That makes it r squared a1. What about a4? What is a4 here? Well, if I look at a4, is r times a3, right? But then isn't this what a3 is right in here? So I can actually write a4 as r times r squared a1, and a4 is r cubed a1. So again, if I expand on this trend that I see, for the subscript 4, the fourth term, the exponent on r is 3, 1 less than that. Okay. So my nth term, therefore, it makes sense that it would be r to the n minus 1 times a1. And this is the formula for the nth term, or the general term, of a geometric sequence. With that, we go to the next definition, and this is what the book gives you. So to find the a sub n, remember a sub n, this is the formula for the nth term, or the general term. That's the nth term. with common ratio r is given by what we have directly above that. Okay, and this is exactly right in here. That's precisely what I have up there. So that's the derivation of this formula. Now let's take a look at some examples just to see how this is going to work out. So in our exercises, we're going to begin with exercise number 12. In exercise number 12, we're given a sequence 5, 20, 80, 320, and so on and so forth. Now think about how we're going about this sequence here as you go from left to right, from first to second to third to fourth, and so on. If I multiply 5 times a number, because this is geometric, we need to multiply by something to go from one term to the next, and so on. So what do I multiply 5 to get to 20? 5 times what makes 20? 5 times 4, correct? How do I get from 20 to 80? Well, that's 20 times 4, isn't it? So you see, each time I'm multiplying by 4, by 4, by 4 to go through the sequence. Therefore, my common ratio here, okay. Now, what is the question asking, by the way? In number 12, the question is, we want to find the common ratio. That's all, pretty simple. So to find the common ratio, therefore, r, what I do personally, I divide second by first term. And that's 20 by 5, and there you go, 4. If you want, you can divide third by second term. That would be 80 by 20, or 4 again. If you want, divide the fourth term by the third term. That gives you 320 divided by 80, and again, 4. So it doesn't really make a difference. Again, personally, I do second by first because it's right up front in front of me, and usually those are smaller numbers, maybe. Or it could be larger, it doesn't matter, as long as there are 2 numbers there. So there you go. We are done with number 12. Let's take a look at number 14. In exercise number 14, the sequence is -5. Next one is -0.5. The one after that is -0.05, and they give us one more, -0.005, and so on. Okay, so again, think about how we can go from -5 to -0.5 to -0.05 to -0.005. How do you think we're going to get there? To go from -5 to -0.5. And we have to multiply. You cannot add or subtract because this is geometric. So there has to be a common rate. Yes, you multiply by 1/10, don't we? Because 5 times 1/10, that's 0.1, gives you 0.5. Now, if that's too much to abstract to think about, then we can go A2 over A1. Remember, this one is foolproof. Second by first, that's -0.5 divided by 5, and you can use a calculator if you like. You get -0.1, or you can do the arithmetic, change 0.5 to 1/2, and you get 1/10 next step, and that's -0.1. Oh, actually it's going to be negative, right? Sorry, -0.5 by -5, so that's going to be positive 0.1, and that's it. We are done with this exercise. Now, in exercise number 22, for this one, the question asks us to find the 9th term. Find 9th term. Now, remember, 9th term for us, it means a subscript 9. The subscript gives you the term number in the sequence, which term. So they want the 9th term in the sequence is 2, 8, 32, and so on. Again, think about how we go from 2 to 8 through multiplication. So you cannot add. You can't say, well, 2 plus 6 is 8. We don't want to add or subtract. We want to multiply. Well, 2 times 4 makes 8, doesn't it? 2 by 4. How do I go from 8 to 32? 8 by 4. The next term would be 32 times 4, wouldn't it? Whatever that is, 132, something like that. So there you go. Now, in order to find the nth term, right, the formula to find a single term, I need to use the formula for the nth term. an is r to the n minus 1 times first term. Okay, now n is 9 here. Whatever the subscript is, see that subscript 9, that's what n is. Okay, so I need to find the common ratio, right? And remember, the common ratio, we divide the second term by first term, and that gives me 4. So the nth term means any term in the sequence is given by r, common ratio 4 to the n minus 1 times first term. First term is 2. And there you have it. So the answer to this one is, this is for any term. Now we want to put the, again, this is what we call the formula for the general term. That's what this is. Now, to make it work for the 9th term, I'm going to go a sub 9, and that's when n is 9. So I'm just going to plug in a 9 in here. C for n, 9 minus 1 times 2. That makes it 4 to the 8 times 2. And 4 to the 8 power times 2, if I did it correctly, I got 131,072. Let me just show you. 4 to the 8 power is 65,536 multiplied by 2. And I got 131,072. And there we go. Pretty large number. That means if you continue multiplying by 4 each time, by the time you get to the 9th term, that term value is going to be 131,000 and change. We are done with this exercise. Now let's take a look at number 24. Okay, in exercise number 24, here the sequence is 2, 2 root 2, 4, and so on. Okay, same kind of question. They want us to find a different term number, the 8th term. So symbolically, that means we want a sub 8, don't we? Because for the 8th term, that's what your n is. N is 8. So first we need to find the general term. The formula for the general term, as before, is a sub n equal r to the n minus 1 times a. Okay, so we're going to actually work this one rather than finding the general term like I did up here. Sorry about that. Like I did up here. Let's go right off the bat. Immediately just put 8 here. We need to find r though, don't we? We need to define that common ratio. So here the common ratio r, again, you divide second by first term. That's the easiest way to do it. Second term is 2 root 2. First term is 2. We can divide out the commons. So it's just going to be square root of 2. That means each time to go from first to second, second to third, third to fourth, and so on, you multiply by square root of 2. So a sub 8 now, that's what we want to do, right? A sub 8 is going to equal r, which is root 2, to the power of 8 minus 1, right? Times first term is 2. A1 is 2. Y, there you go. First term right up here in front of number 24. This is 2. So that's what A1 is and goes right in here. Now we need to work the radical here. And let me work this radical for you separately. 8 minus 1 is 7, right? So you have root 2 to 7th power times 2. Now let me do root 2 to 7th power over here. Root 2 to 7th power, that's equal to root 2 to the 6th power times root 2, right? That means there are 7 factors of a square root of 2. It means the square root of 2 times the square root of 2 times the square root of 2, and so on. 7 times. Now, square root of 2, that's 2 to 1/2 as a rational exponent, times square root of 2. Using the power rule of exponents, I can now write in here, I can multiply 6 times 1/2, that's 2 cubed times root 2, and 2 cubed is 8. So there you have it. Root 2 to 7th power ends up being 8 root 2. Notice 2 cubed, don't multiply 2 times 3. 2 cubed means 2 by 2 by 2, right? That's 8. So it's 8 rad 2. Therefore, I'm going to write this as 8 rad 2 times 2, right? That's this 2 right up directly above it. 8 by 2 is 16, and 16 root 2 is the answer to this exercise number 24. That's where the answer is. Okay, and we are done in this segment, not the section, but just the segment. Let's take a look at number 30 now. Okay, in exercise number 30, the question reads, let me go right in here, exercise number 30. In this exercise, the question says, find the nth or general term of geometric sequence. Just going to put that symbolically, find a sub n. That means the general term. Now in number 30, the sequence is 2, 4, 8, dot, 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 means so on and so forth. This is an infinite geometric sequence. So the formula for the nth term is given by, again, r to the n minus 1 times first term. So r, I need to find r. Remember, second by first. R is 2. Again, this means to go from 2 to 4 to 8, next 16, next 32. Each time you multiply by 2 to get to the next term from previous term. So r is 2. So I'm going to go ahead and put 2 in here. That's r. To the n minus 1. For the nth term, we don't know what n is, so we're going to keep n in the exponent. Times. First term is 2, right? That would be, let me use color in blue. That's this 2. That's our first term, right? First term is 2. It's just coincidental, folks, that our first term, and sorry about that, that our first term and common ratio are the same. Pure coincidence. Okay. Now, you can actually work this a little bit. If I actually give this to an exponent of 1, remember the multiplication rule of exponents kicks in. This is the multiplication rule. A to the m, a to the n is a to the m plus n. So, because I have 2 to the n minus 1, 2 to the first power, the bases are common. Here's a common base. And you actually combine the exponents, right? Now, negative 1 plus 1, those add to 0, and the final answer here is actually 2 to the n, and that's what a sub n looks like. Again, what good is this for, this formula? You can plug in any number you like. For example, if I want to know what is the 5th term, you plug in a 5 for n. So I'm going to do 2 to the 5th power here, 2 to the 5th power, and that's going to give me that. Okay, which is what, 32. You want to know what the 1000th term is, you put in 1000 and so on. That's why it's called a general term. It keeps it in general. An interesting one is number 31. Let's take a look at number 31. Number 31 we actually saw in the previous section, so that's why I picked this one. But the way we worked it in section 14.1, let me reference to section 14.1. In fact, if you look at the video lecture for section 14.1, this was one of the exercises we did. In that section, we looked for a pattern. Remember that business of looking for a pattern? We looked for pattern, and that's how we got the answer. And I believe the answer we got was negative 1 to the n minus 1, right? That's what we got. That was a sub n. Again, this is using method of section 14.1, looking for a pattern. Now, let's view this differently. This time we're going to see this as a geometric sequence. Why? Because we are told for one thing, it says find the nth term of a geometric sequence. So, if it's geometric, means there is a common ratio. Remember, we do a2 by a1 to get that fixed ratio. So that's negative 1 divided by 1, which is negative 1. So there's my common ratio. And what was the formula for the nth term? Let me just write the formula once again. It's a sub n r to the n minus 1 times first term. Okay. Now, in this formula, we need to plug in our first term is 1. The common ratio is negative 1, right? we're going to plug those into our formula for the nth term. So a sub n is going to be r is negative 1, to the power of n minus 1 times a1, first term is 1. Now 1 times any number is the number itself. So here, from this, I get a sub n is equal to simply negative 1 to the n minus 1. And we got exactly the same results that we got up here, except different approach. Again, section 14.1, we looked for the pattern and we pretty much guessed, correct? That's how we did it in that section, by guessing. In this section, we're actually using the fact that this is a geometric sequence, and we use the formula for the nth term. Okay, and we are done. Not with the section, but again within that segment. Now, one other thing we're interested in this section is the idea of what we call the nth partial sum. We did this in section 14.2 for an arithmetic series. So let's take a look at and see what the formula, can we derive a formula for it. Now I'm going to go ahead and derive this formula. You're not responsible for the derivation of the formula, but in the end I'm going to box the formula which you actually need. The formula is all we need out of the work I'm about to do. But it's interesting, how do we come up with the formula? Okay, so just bear with me for a few minutes until we get to the formula you're going to need to do the exercises. So here is what my geometric sequence looks like, right? A1, A2, A3, and so on. At some point here, I'm just going to put a sub n minus 1 and a sub n. We're going to make it a finite sequence. And again, a sub n means the nth term, a sub n minus 1. Right, this is the nth term, and a sub n minus 1, that's just the one before it. Isn't that n minus first term? There you go. That's what that is. Now, each of these, remember, each of these we can write it as a multiple of that common ratio. So a2, you multiply r times a1. For a3, you multiply r squared. We derived these earlier, times a1. Again, notice the idea is to use first term. So every term is stated in terms of the first term. So for the n minus first term, actually this is going to be r to the n minus 2 times a1. And for the nth term is r to the n minus 1 a1, the formula that we derived. Right? Again, note, see subscript 1. So every term up to the nth term is stated in terms of a1. Now, if I look at the nth partial sum, so here's the nth partial sum, s sub n. That means sum of the sequence that gives me this series. So I'm going to do a1 plus r a1 plus r squared a1 plus dot plus r to the n minus 2 a1 plus r to the n minus 1 a1. Right, I just added the first n terms. That's all that means. Now, this expression that I just have, okay, the expression I just wrote, this expression, let's multiply this expression by r. Okay, so I'm going to go r times s sub n. Now, when I multiply that expression by r, everything now is going to have r attached to it, right? So it's going to be r a1 plus, well, r, there's a red r, and then there's another r a1 here, right, which makes it r squared. Next one, now I'm going to write it, is going to be r cubed a1 and so on. Now r to the n minus 2 times r, that's going to be r to the n minus 1, right? Because r to the n minus 2. Multiply by r, common base, add the exponents, and we're going to get n minus 1. So that's how I got this last expression. a1 plus r times r to the n minus 1 is just r to the n, and then a1. Okay. Now, so this is what that expression looks like. Next, what we want to do is we actually want to now subtract. Okay, so we have these two expressions, right? Got this one and we have that one. Let's do S sub n minus r S sub n. In other words, we're subtracting the bottom expression from the top expression. So that's going to be a plus r a1 plus r squared a1 plus dot 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 plus r to the n minus 1 a1, right? That's the first one. And then we're going to subtract. That's going to be minus the second expression is, I'm going to line these up, ra1 r squared a1 plus r cubed a1 plus dot 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 r, oops, sorry, there you go. That's going to be r to the n minus 1 a1 plus r to the n a1. Okay, so again, I copied that second expression. I copied this all of the right side right in here. Okay, now if you note in here that we have actually a few like terms, and because we are subtracting here, so what happens next is that this ra1 and minus that ra1, those actually add to 0. There's going to be an r squared a1 term and r squared a1 term here. There's going to be another term up there, r cubed a1 down here cancel. So it looks like everything from the top, from here on out, like this one and this one, add to 0. So all that actually remains in the right side is this a right in here and r to the n a1 from down here, right? It's going to be a, and all that remains is this one. But remember, there's a subtraction in front of parentheses, so this is going to actually become a minus, or a1 actually, sorry, drop the subscript there, r to the n a1, and the left side is r s sub n. There you go. Now on the left side, let's factor s sub n, and that's going to be, when we factor it, it's going to become parentheses 1 minus r. The reason there is a 1, because you can think of 1 times that, and then you actually remove s sub n from these two terms, right? You factor it outside, all that remains is a 1 and a negative r. Okay, and that's going to be equal to the right, I'm going to factor a1. It's going to be 1 minus r to the n, and we are almost there. Next step, I want to actually isolate s sub n. So let's divide both sides by 1 minus r. So that means the formula for s sub n therefore is going to be a1, 1 minus r to the n, divided by 1 minus r. And there you go. Here we have again a formula for the nth term. So this is what you actually now want to know. Again, this was all the derivation of it for those that are interested. If you're not interested in the derivation, you can just look at the final result. And that's what that is. And there you go. So that's what you see here. To find the nth partial sum for the geometric sequence, so the sum of the first n terms, that's what s sub n means, right? This s sub n, what does that mean? That means this, the sum of the first n terms. That's how we write it. For the geometric series is given according to this formula. Now, here we have r cannot be equal to 1, because if r is 1, you get 1 minus 1, 0, and division by 0 is undefined. So it's for that reason. Okay. And here is the formula for the nth partial sum. Let's take a look at an exercise here. So we're going to look at exercise number 36. In exercise number 36, the question reads, use the formula for s sub n to find the indicated sum for each geometric series. In number 36, they want to do S sub 6 for the geometric series is 16 minus 8 plus 4 minus so on and so forth. Now remember, S sub 6, that means we want to add 6 terms in this sequence. Okay, so we have a formula directly, you're looking at it above this expression. So when n is 6, I'm going to put 6 here. Okay, S sub 6 is equal to A1, or A1 is what, 16. The common ratio, you divide second by first term. That's negative 8 by 16, and that gives you negative 1/2. That's the common ratio. So again, to go from first to second, you multiply 16 times negative 1/2, you get negative 8. To go from negative 8 to 4, you multiply negative 8 by negative 1/2. It becomes 4, and so on. Okay, so the next term after 4 would be what? 4 times negative 1/2, and that's negative 2, right? All right, so let's work this formula now. First term, a sub 1, that's 16 times 1 minus common ratio was negative 1/2 to the power of, it's going to be 6, right? To the nth power. And I'm going to close parentheses. Maybe I should have used brackets here. Let me do that because it makes easier to see these. There you go. Parentheses may run together. Now in the denominator, I have 1 minus common ratio. That's 1 minus negative 1/2. So let's work the fraction now. I'm going to do that on the side here, actually. First of all, negative 1/2 to the 6th power. That's like negative 1 times 1/2 to the 6th power, isn't it? Which means negative 1 to the 6 times 1/2 to the 6. Well, negative 1 to even power is 1, so that's just 1. And 1/2 to the 6, that's 1/2 times 1/2 times 1/2, and so on. That's 1/64. So that's just 1/64. So in the numerator, I have 16 times bracket 1 minus 1/64. And in the denominator, we have 1 minus a negative 1/2. Well, 1 minus negative 1/2, that makes it positive 1/2. That makes it 3/2, doesn't it? 1 and 1/2 is 3/2. Now, in the numerator, I have 16 times 1 minus 1/64. That's going to be, let me move this up a little. So that's going to be 3/2. 1 minus 1/64, well, that's 63/64. I know fractions are a pain in the neck, right? Like, we really like fractions. And there you go. Now, how is this going to work out? Well, we're dividing, true? We're doing division, fraction by fraction. So I'm going to invert and multiply the 16. I'm sorry, the 3/2. So that's 16 times 63/64 times invert and multiply, it becomes 3/2, right? Ah, that was tricky. Invert and multiply, it becomes 2/3. I did that on purpose. Okay. Now, we can actually simplify some things here, can't we? So for instance, 2 times 16, 32, divided by 64, that makes it 2 on the bottom. 3 and 63, we can divide the 3's out, and that's 21. So all said and done, in the numerator, I just have 21, and in the denominator, I have 2. So the answer is 21/2, and 21/2 is equal to 10.5. So if you add up the first 6 terms, that's the sum of the first 6 terms. The answer is going to be 10.5. That's what the nth partial sum formula is good for. Hopefully you followed this exercise. Let's take a look at number 40. Now, if you need, by the way, to, like, you know, you don't have to go in my pace. You can actually rewind the video from the beginning and watch how things unfold from the beginning. to pace yourself, so it goes according to your pace rather than my pace. Okay, let's do S sub 10 in number 40. S sub 10, and we want to do this for the following. S sub 10 for. The expression is 1 plus x squared plus x4 plus x6 and so on. Okay. So, this sum of the first 10 terms. So again, this is geometric. I need a common ratio, and we need the first term, right? The common ratio is x squared over 1, or just x squared. The first term is 1. True? That's the first term, and that's where that comes from. So that's just the 1 here. Now, let's use our formula for the nth term. S sub n, again, is a1, 1 minus r to the n, divided by 1 minus r. Now in here, this is going to be, first term is 1, 1 minus, common ratio is x squared, and we're going to raise that to the nth power, divided by 1 minus common ratio of x squared. In the numerator, this first one times the parentheses, so we can just drop the 1. Within parentheses, here, inside, we have x squared to the n. Right? We can use the power property of exponents. We actually multiply 2 by n, correct? So that's going to be 1 minus x. 2 times n is 2n. And the denominator is 1 minus x squared. Right? This is again for any n. But in this exercise, n is 10, isn't it? Right? N is 10. How do we know? Because it's right in front of number 40. It's written S sub 10. So in this exercise, when n is 10, so S sub 10 is going to be 1 minus x to 2 times n, 2 times 10, and divided by 1 minus x squared. So that's going to be 1 minus 2 by 10 is 20. Divided by 1 minus x squared. And there you have it. And we have the answer to number 40. This is actually the answer to number 40 right in here. That's what that is. Okay. So again, hopefully you follow that exercise. So, are we done? No. We got one more idea in this section. And in this, once we're done with this idea, we're done with this section. Now, let's take a look at infinite geometric series. That's what we want to look at next. So, infinite geometric series. Infinite geometric series is just that. It's a series where there are infinitely many terms in it. So give you an example. Let's say my sequence, first of all. Sequence is like this. 3, 6, 12, 24, 48, and so on. So I randomly started 3 starting point, right? So this is a geometric. That's what I had in mind. And my first term, I said, let's start with 3. For common ratio, I said, let's double up each time, multiply by 2 to go from left to right. So 3 times 2, 6. 6 by 2, 12. 12 by 2, 24, and so on. Now, if you look at this, 6 is greater than 3, right? 12 greater than 6. 24 greater than 12, 48 greater than that. So here, the successive terms are getting larger, right? Terms are getting larger. Now, when these terms are getting larger, if I want to actually add these up, and I know there's infinitely many terms, right? See that dot, dot, dot? So if I actually want to find a series that goes with this, that's called S. That means I got to do 3 plus 6 plus 12 plus 24 plus dot, dot, dot. Now, because each term is getting larger and larger, I really cannot add these to infinity, can I? We can, because the sum is getting bigger and bigger and bigger. So in this case, the correct terminology, we say the sum diverges. That means it's getting bigger and bigger. We cannot, in other words, let's say instead of cannot find the sum, let me just write it this way. The sum does not. Okay, it doesn't exist because they're getting bigger, bigger, bigger. So this series is no use to me, right? I can't really use this series for anything to find. If I want to find the sum to infinity, I cannot. I can do the nth partial sum, couldn't I? Like if I want to add the first 4 terms, 5 terms, 50 terms, those you can, but I cannot add to infinity. All right. Now let's take a look at another sequence. This second sequence that I have, it's going to look like this. My sequence is 10, 5, 5 halves, 5 fourths. So what I'm doing now is actually, as you go from left to right, to go from 10 to 5, I multiply by 1/2 times a half. Each time you multiply by half to get to the next term. So this is a geometric sequence where my first term is 10 and my common ratio is a half, right? Because each time I multiply by half. Now, again, you can divide second by first, 5 by 10 to get that 1/2 also. Now, one thing you can notice about this sequence, here, terms are getting smaller, right? As you go from left to right. Well, if the terms are getting smaller, right? Each successive term is smaller than the previous term. Well, then actually here the sum, we may be able to find the sum to infinity of this one. Okay, so what does the sum to infinity of this one looks like? Therefore, the sum equal S. That means 10 plus 5 plus 5 halves plus 5 fourths plus dot, dot, dot. Now, of course, we're not going to grab a calculator and do this, right? Because we are adding to infinity. We cannot do this. So in this case, because the terms are getting smaller, what we say is that the sum actually exists. Now, in the case where the sum does not exist, okay, here are some of the ways we can say a sum does not exist. We can say these are all the AKAs for the sum doesn't exist. We can say the sum cannot be found, right? Because they're too large. I'm looking at again the example directly above this one, the one we just did. And we can say the sum approaches infinity. All these are telling the same thing. All of these so far means the sum doesn't exist. We can say the sum is about converging to a number. And also some say the sum, let me move this below. And we can also say that the sum grows without a bound. This sum grows without a bound. It keeps getting bigger, 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 and bigger. So all of those mean the sum does not exist. I'm just trying to give you some terminologies about this. Now, what if, this was a spoiler, that's okay. Now, what if, let's take a look at the case, and the reason, by the way, this here, this one doesn't exist is because the common ratio here is greater than 1. Now, let's see what happens. We're going to derive now the theoretical work for the case where actually the common ratio is less than 1. But let me show you an example here, okay, before we actually generalize the theory. Let's say my common ratio is 1/10. And if I square this, I get 100ths, right? 0.01. If I cube it, I get 1000. That's 0.001. If I raise it to the fourth power, it becomes 0001, doesn't it? That's 1 over 10,000 and so on. So imagine if I do r to the 10th power, that's going to have 1, 2, 3, 4, 5, 7, 9 zeros and a 1. So if you look at these numbers, what's happening is that the number is getting close to 0, isn't it? Close to 0. So what we're saying is that, in fact, we can say that r to the n means 1/10 to the n is approaching 0. Okay. Now, if r to the n is approaching 0, and again, the reason here is that your r is less than 1. That's why. Now, the common ratio could be positive or negative, by the way. Okay. So if I give you an example of a common ratio that's negative in here. Okay. Common ratio that's negative here. Let's take a look at this example. This time I'm looking at r equals -1/2. I still want it to be less than 1 in absolute value. This time I'm looking at -0.5. So if I do r squared, well, r squared is going to be what? 0.25? That's -1/2 by -1/2. r cubed, that's -0.5, 0.5, 0.5 is -0.125. So you can see that this is also getting smaller, isn't it? R to the 4th is going to be 0.0625. And r to the 10th power, for example, is going to be 1 over 1024. Okay, which is going to be less than 1000. 1 over 1024 is actually, the number is going to be this, 0.00098. So again, notice what's happening is that this thing is approaching 0. So this is going to happen anytime absolute value of common ratio is less than 1. Again, absolute value because r could be negative. So, but we just showed in the case of positive, negative, it doesn't matter. It's either positive getting close to 0 or negative fraction getting close to 0 on either side of 0. So we can generalize this. Therefore, we can say the following. Note: absolute value is less than 1, then r to the n approaches 0. The arrow here means arrows. Okay. Now, let's actually revisit, and let me move these out of our way, actually. Hold on, let me pause and move these over, and so I don't have to waste your time. Okay, I'm back. So now let's revisit. Let's take a look at the formula we had for the nth partial sum. Remember S sub n, it was a1, 1 minus, here is the r to the n divided by 1 minus r. Now, imagine in here, as n becomes very large, okay, as n becomes large. How large? That large. Means it gets to be near infinity. Millions, billions, trillions, whatever that n might be. Very large. So r to the n approaches to 0, right? And if absolute value of r is less than 1, then what happens is this expression right in here, that part becomes 0, right? This goes to 0. So the expression actually at that point looks like this. Well, we're going to adjust the subscript to s sub infinity, because now we are not adding n terms, you're adding infinite number of terms. It's going to be, well, 1 minus 0 in the numerator is 1, multiplied by a1, divided by denominator. So we actually get this very simple formula, much easier than the formula for the nth partial sum. Okay, and this formula is actually known as the sum to infinity formula. Sum to infinity. So again, to make a long story short, if the absolute value of the common ratio in a geometric series is less than 1, it turns out we can actually add the series. We can add the sum to infinity. Now, although the theory says that it has to be infinity, right? Large meaning infinity. But in practice, and I'll show you an example, it really doesn't need to be that large in order for this sum to converge to a number. Okay, so that's what this is. So, and this is what this expression, that's what this definition is calling for. Okay, so in this definition, now the book calls this the limit of an infinite geometric series. They talk in terms of limits. Okay, the limit here they're talking about this limit is the sum. The limit equals sum they're talking about. So think about the limit means the sum of an infinite geometric series. So if absolute value of r is less than 1, the limit, meaning the sum, is given by that. Notice again the subscript here is infinity. And do a blow up on that. That's what that symbol is, infinity. Okay, and what if the absolute value of common ratio is 1 or bigger than 1, then there is no limit. The sum will not exist. Okay, so that's what these are. Let's take a look at now an example, an exercise. So we're going to look at exercise now number 44 in your book. In this exercise, you're given 80 plus 20. We're given a series, 5 plus 5/4 plus dot, dot, dot. So we're given an infinite series. The question actually, number 44 reads, determine whether each infinite geometric series has a limit. Remember, limit means sum. Does it have a limit means does it have a sum? If a limit exists, means if the sum exists, find it. So that's what we want to do. Now, in order to determine, before we can actually find the sum, it's imperative, very important, we find the common ratio. A2 over A1, that's 20 over 80, which means 2 out of 8, or 1 in 4th, right? Absolute value of 1/4, which remains 1/4, right? Absolute value of positive numbers are positive. That is indeed less than 1. 1 is the magic number here. So we can say the limit, meaning the sum, the limit exists. Okay, the limit exists. And now we want to find it. So now we're working on the find it part. Find it. So how are we going to find it? Well, the formula, you're looking at it, I'm scrolling it up a little bit. So the sum to infinity is a very simple fraction, a1, 1 minus r. Boom, there you go. What is a1? A1 is our first term, 80. 1 minus, common ratio is 1/4. Well, 1 minus 1/4 is 3/4, isn't it? And in this case, we're going to invert and multiply. We get 4/3. When you invert 3/4, you get 4/3. 4 times 80, 320 divided by 3. Now this sum, 320 divided by 3, I'm just without a calculator. That is 107 and change, right? Rough. Actually, it's not 107. If it was 321, it would be 107. So it's 1/3 shy of 107. So there you go. To make you happy, it's 106.67, more exact. But that's not the point. The point I want to make is actually, this is interesting observation. If I add, remember this assumes n goes to infinity, right? We're looking at sum to infinity. But look at this, only first 4 terms. If I add just 4 terms in this series, that means 80 plus 20 plus 5 plus 5/4, isn't it? That's going to give me what, 106.5. Wow, check this out, folks. Only 4 terms count for entirely almost that sum to infinity. That means from the fifth term all the way to infinity, you're only picking up the difference between 0.67 and 0.25, right? That's how much is what we don't have. There you go. This is how much sum there is to infinity beyond the fourth term. Isn't that impressive? That's very cool. So anyway, that means in technical terms, what that tells me is that this sum converges. True, converges means you can find it. It comes to a point, it comes to a number. But it converges very rapidly. So that's what's interesting about it. And this really makes these series very useful, by the way. Hopefully, for some of you that take higher math, infinite geometric series are one of the most important form of series that are used in calculus courses. Okay, let's take a look at number 48. In number 48, we have another example, 2 plus 3 plus 9 halves, plus dot, dot, dot. Same question. Determine if the series has a limit. Remember, we need to find the common ratio. Second, my first term, that's what doesn't mean the sum exists. What's important is the fraction has to be less than 1. So, is 1.5 less than 1? No, clearly not. Because it's not, then we say sum does not exist. And actually what we mean is this: not only sum, but sum to infinity. To infinity. Now I can always add the first 4, 5, 10, 20, 50 terms, right? However many finite terms, but we cannot do it to infinity. So I'm not allowed to use that formula. We stopped. We're done. The sum does not exist in this one. And we put a happy face on that. Okay, let's take a look at one more, and then we're almost done, folks. We're going to close it with an interesting exercise. Okay, but before we look at that interesting exercise, let's take a look at one last exercise, and that is number 50. We're going to look at number 50. In number 50, the series -6 plus 3, -3 halves plus 3 quarters, negative so on and so forth. Same question. Does the limit exist? If it does, find it. Common ratio, second term by first term, -1/2. See, the common ratio could be negative. Now for this one, absolute value of -1/2 is 1/2, isn't it? And that absolute value is less than 1. 1 is the magic number here, folks. It is less than 1, so that tells me the limit exists. Remember, limit means sum. All right, so let's find the sum now. How do I find the sum? I need the first term, don't I? First term is -6. That's right up here. There. And we're going to use the formula. We have a simple formula. Sum to infinity is first term over 1 minus common ratio. A very simple fraction that we can use. So first term, a sub 1, is going to be -6 divided by 1 minus the common ratio. Common ratio was 1/2. Actually, -1/2. Sorry about that. That's going to be, let me use blue, -1/2. And there you go. That's what the common ratio was. Now, in the denominator, see we have double negative here, right? Double negative makes positive. So this is just going to be -6. We're going to add a half and 1. We get what this. To divide by a fraction, we're going to invert and multiply. So that's -6. And of course, next step, 3 and the 6. We divide the 3's out. -2 by 2 is -4. And there's the answer. -4 is the sum to infinity. If you add these terms to infinity, it's going to be -4. And again, you can add just the first 4 or 5 terms. You'll see that you're already almost at -4, which is very impressive about these series. Okay, almost done. Now you're getting tired of it. If you are, just pause the video, go out and get yourself some cappuccino or coffee, juice, whatever makes you happy, and then come back and restart the video. Now let's take a look at this last exercise. I did not assign this exercise, but this is interesting just to see the utility or application of what we're doing, something that's fun and entertaining. Now suppose you're offered a lucrative job. This lucrative job that you just found, graduated from Mesa College, from four-year university, you find a job. And your job is going to hire you for just the month of February. How's that? It's a temporary job. And they're going to start you at a whopping 1 cent, a penny, your first day on the job. Very lucrative, right? But here's the catch to this. They're going to double your pay as the days go by. So on the first day, you make 1 penny. Second day, let me write these. Here's your first day pay, 0.01. Second day, you get 2 cents. Then they double that, you get 4 cents, 60 cents. So notice 1, 2, 3, 4, 5, 6. After 1 week, your salary is 64 cents a whole day. Okay. Now, if you add these up for the first week, by the way, look, you made almost $1, less than $1.50, right? Which is an impressive visit. But the question is interesting. The question is, suppose this doubling goes on for the whole month of February, which are 28 days in. Okay. How much would you earn at the end of the month? Okay. Well, you can see from the way I have written this series, plus dot 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 plus a sub 28, right? Because there are 20 days in February. So we want to know what this is. So again, this is going to be a geometric series. The common ratio is 0.02 divided by 0.01, means double. They double your pay every day. What is your first term? A whopping 1 cent, $0.01. Now, let's take a look and see how much you're going to make. This is a finite series, right? S sub n, A1, 1 minus r to the n over 1 minus r. Okay. Now, let's plug in for these. S sub, remember 28 days in February, so S sub 28 is. Your first day pay is 0.01. But then check this out. Your common ratio is 2. Right? That's 2. Let me not use red because I already used red for the subscript. Okay. Let me use green. It's going to be 2 to the nth to the 28 power. Check this out. That's a huge exponent, isn't it? Once you do 2 to that 28 power, it's going to be very, very big. Okay. And there you go. That's what I have. Now, here's 0.01 on the outside. The denominator, 1 minus 2 is -1, isn't it? The numerator is 1 minus 2 to the 28 power. Now, you can do on the calculator 2 to the 28 power minus 1. So the numerator, you can check me. Use your calculator, you see. That's going to be 268,435,455. Check that number out, folks. And it multiplies by 0.01 in front of it. And that number is after the month is over. You have made $2,684,000, 354 cents and 55. And if you are interested, you can actually write this series. I've written the first 6 days, right? Keep writing this up and you will see the lion's share of that money comes in the last week. Right up until almost third week, the employer is very happy to have you at 1 cent starting pay, doubling your pay every day. But the last week is when they're probably going to go broke. So anyway, very impressive. About $2.7 million. So this is just an application. Interesting, maybe not realistic, but just an interesting application of geometric series. So we're done with this section, folks. Again, if you need to, you can rewind the video, go back to the beginning, and you can slowly watch the video, pause it wherever you need to before I go to the next step, and see if you can actually guess what the next steps are as you watch the video. This way you can pace yourself according to your progress. Okay. Now, with that, we're done with this section. We only have one more section which the next lecture is going to address. That would be section 14.4. But we are done in section 14.3, geometric sequences and series.